and then we will move on to 10-4 a little bit today. The examples we did yesterday, guys, they gave you, and I think these are the easier types when they give you the perimeter or they give you the apothem, and you only have the task of finding the other component. So they give you the apothem, you have the task of finding just the perimeter. Or they give you the perimeter, you have just the task of finding the apothem. I think the hardest ones are of this version here, where they give you the radius, you have to find the apothem and the perimeter. Okay, because you got to do two things here. There are a handful, and I would say upwards of 10 to 15 example problems in video format that you go look at on the website, provided you have trouble over the weekend doing any of the homework. Okay? There are some things that I want to talk about in regards to just the setup of these things. The formula, always 1/2 AP. Okay? Always 1/2 AP. Now, you may get stuck from time to time, and I want to answer it. All right, so the issue I've had with people in the past is that they forget this formula and they Google. They get to a question on their homework, say Google area formula for a hexagon. And it comes up with something different. And it works. There's another formula for the area of a hexagon. Okay? Or they Google area formula of an octagon, and they find something that is not 1/2 AP, and that's fine. There are formulas for those other shapes. Okay? But would you rather remember an infinite number of formulas for varying shapes, or one formula for an infinite number of shapes? You'd rather know one formula for any amount of shapes, right? Does that make sense? So 1/2 AP is the best formula we can come across for all of these polygons. Okay? However, if I want to Google hexagon formula, it might show up something different. If I Google octagon formula, it might show up something different. There are alternative ways of maybe doing some of these things. But 1/2 AP is the most efficient way of addressing all your polygons, a regular polygon. Okay. The problem with this picture is that, does anybody want to draw an 11-sided figure? No, sir. No. Okay. I don't even like drawing 5-sided figures. Okay. But let's look at this picture here. Let's look at this right here. Okay. I've got a 12-sided figure. Okay. Does that 12-sided figure have a circumscribed circle, right? Okay. So each one of those black lines is the radius of the circle, but it's also the radius of the polygon, right? Okay? And that's going to be the case no matter which one of these polygons I talk about. Okay? That radius of the polygon is the same as the radius of the circle. So when it says the radius of the circle in our problem was 12, then the radius of our polygon is also 12, right? Okay? Now, that polygon, that 11-gon, does it have a blue triangle in it? See this blue triangle here? Okay, that red segment, you can't really see it very well, but that red segment, is that, what do you call that red segment for this figure? That's the apothem. Does every other figure that we talk about here have the same blue triangle and the same red apothem? Yeah, okay? So as you do these questions, I don't care how many sides they tell you. I'm going to zoom in. I'm going to just kind of look at this picture here. I'm going to have a side that comes down to another side that goes up to another side, right? And in this middle side here, I'm going to draw my apothem straight up, and I'm going to draw my radius down to the vertex. And if I had a 10-sided figure, does that picture kind of seem the same way? And if I have a 9-sided figure, is it the same way? 10-sided or 8-sided, the same way, right? Okay? And even though I go beyond 12, it's going to be the same. It's just that these sides just kind of flatten out more. So, when we do this, and you're going to see me in all the examples that I go through in the videos or, the ones we do together in class, you're going to see this picture drawn a lot. I just want to make sure that you understand what I'm doing here. This is going to be the side of my 11-gon. That's a second side, and that's a third side, but I'm not drawing the whole thing. This segment here is going to be called my what? Apothem. And this thing here is going to be my radius. So there's my apothem. There's my radius. This here, I'm just going to call it X for now. But isn't that X going to help me find a side length? And once I find that side length, isn't that going to help me find my perimeter? Okay. So that's the picture that I always set up with these, no matter how many sides I've got. Here they're telling you your radius is 12, right? Do you guys remember the formula for finding that angle? Okay. I'm going to say 2n, but 2x is fine. But I've already got x down here, something else. Excuse me. And n is the number of sides you have, right? So it's an 11 gone. So it's going to be 360 over 22, which reduces to 180 over 11, or as a decimal, 16.36 repeating degrees. And both those are actually degrees. Is that okay? That's that angle. Yesterday we did hexagon, we did triangle, we did square. Those were 30, 60, 90, or 45, 45, 90 stuff, right? Here it's not. So here, if I get something that's not 30, 60, 45, I have to use SOHCAHTOA, right? So let's set out to find the apothem first. What side would the apothem be here for that red angle? It'd be the adjacent side. What would 12 be? Hypotenuse. Which trig ratio, sine, cosine, or tangent, uses adjacent and hypotenuse? Cosine. So I'm going to say cosine of 16.36 is equal to A over 12. That's going to eventually give me A to be 12 cosine of 16.36. Is everybody okay with that? Just multiply both sides by that 12, right? Now that's rounded. So if I write it this way, that's the exact. Does that make sense to everybody? I want to talk about maybe the process of, or the reasoning maybe of why we would do that. And leave it as 18 or 180 over 11. Let's do this one. So we now know the apothem. Let's now find this distance down here of x. So what side is x in regards to the red angle? Opposite. Is 12 still the hypotenuse? Okay, so what uses opposite and hypotenuse? Sine. So sine of 16.36 is equal to opposite over hypotenuse. So that's going to give me x to be 12 times sine of 16.36, right? And that is just that purple distance. Is that okay with everybody? What do I need to do with that number to get a side length? I need to double it. So let's put A times 2 out in front here. What would I then need to do with that to get my perimeter? Times it by 11, so I'll put that out in front. Does that make sense? So that's doubling it and then multiplying it by 11. Now, which of these numbers? This is a number, that's a number, that's a number. Those are all rational numbers, right? That's also a number, but that's irrational, right? Which ones work the best together? 11, 2, and 12. Let's multiply those together, and you get 264. So x equals 264 sine of 16.36, or 264 sine of 180 over 11, right? Now, so x was just this blue stuff. X was just that blue stuff. When I doubled it, x became a side, right? Does that make sense? And then when I multiplied it by 11, a side became the perimeter. Does that make sense, everybody? So this here is actually the perimeter. All right. So now do you have A and P that you need for your formula? And my hopes are you see the reason why this is a harder type of question. Generally speaking, if they gave me the perimeter, I would only have to do the work up there for A. Or if they gave me A, they gave me the apostrophe, I'd only have to do the work down there for P, right? But if they give me the radius, I got to do both situations. Okay? So now I'm going to go back to my calculator. And let's see here, decimals. We're going to type in 1/2. Okay? Now it was 12 cosine. I'm going to type in 16.36 first. And then 264 sine 16.36. And it evaluates it and it tells me my area of this shape is 428, right? Now 16.36, what did we do with that number? We rounded it. So that's not an accurate answer, right? Okay. If I were to take this and write it this way, 180 over 11, 180 over 11, now I didn't round any of those numbers, right? So that is the exact answer out to that last two that you see up there. Okay? A better answer, right? Okay? If you're a person that says, well, you've been talking about multiplying rational numbers. That's a rational number. That's a rational number. That's a rational number. Why can't we write this as, I think it's 1584, cosine of 180 over 11 times then sine, I don't want those extra parentheses there, sine of 180 over 11. Does that give you the same answer? So that 1584 is 1/2 times 12 times 264. So you can write it that way if you want an exact answer. Does that make sense to everybody? In trigonometry, we learn that that expression right there can be rewritten a lot simpler than what we see it right now. And that's kind of what, if you're interested in trig, that's kind of where we kind of extend what we've learned in geometry. Okay? So this is the best answer, correct? No rounding there, correct? Okay? If I was on Math Excel or the end of course exam and they said round to the nearest hundredths place, am I wrong by that top one? Yes. Yeah, the top one says 10, right? 0.10. The actual answer is 0.187, which we would round that to 0.19, right? That's what the end of course exam or Math Excel would be interested in. Okay? Now, how can I make this better? How can I make this number up here better? Round further out. So go 3/6 there and 3/6 there, right? Because it was 3/6 repeating. Is that a better answer now? Yeah. So my hopes are you see the further I round my intermediate values, as those are used inside multiple operations inside my formulas or whatever, the further you round them, the less you impact the tenths place, the hundredths place, the thousandths place, and so forth, right? So as you're working on the end of course exam, I know people are going to do this. I know you're going to do this on Math Excel. I know some of us are of this nature, and there's nothing wrong with this. But some people are going to say, okay, you just found 12 cosine of, we said 16.36, and I know somebody's going to round that 16.4. And that's your apostrophe. And I know somebody's going to say, well, my apostrophe is now 11.5. And then they say, okay, well, let's go 12 sine of 16.4, and that's that x distance, and they're going to say, okay, that's 3.4. We're going to double that, and then we're going to multiply that by 11, and there's my perimeter. And they're going to go 0.5 times 11.5, that's my apostrophe, times my perimeter of 74.8, and they get that number right there for their area. And then when we get back to Math Excel or the end of course exam, and they ask us to be accurate to the tenths place or the hundredths place or something like that, we're not even close in terms of the tens here now, right? Okay, we're 428 and 430 they're pretty far off. Okay, so you can see how much rounding we did here and how that impacts the actual answer, right? My fear is that we had some people that are going to do this because it's I think logically it makes sense to do it that way. It makes sense to get concrete values for A and P as we move through instead of leaving them as 12 sine of 1636, right? Okay. But be careful if you're going to do that. If you're going to do that, nothing wrong with it, but don't go 11.5. Go 11.51043, however many decimal places out. Does that make sense? If you know your answer is going to be 1 into the 10th place or the 100th place, go out with your intermediate values 4 or 5 decimal places so that the 10th place or the 100th place is not impacted. And that's a pain in the butt, okay? Because there's a lot of situations where you would round, right? So that becomes too tedious eventually, and then you find the benefit of leaving it as 180 over 11, okay? Because you can bypass all that stuff if you work with exact fractions, okay? So make sure you understand that. Now, this is the reason I talked about 5 years ago. I didn't talk about this. 5 years ago, this was not important to talk about in regards to passing the state test, because that state test 5 years ago is a multiple choice. And if you go through this, and multiple choice answers had like 428, 510, 570, and 310 on it. Okay, and you came up with 430. Would you know that the 430 is going to match up to the 428? Would you be confident in choosing the 428? Okay, that's awesome. You could have done that, and we wouldn't have had to talk about this. But now, the end of course exam, it's going to be like Math Excel. You're going to type in the boxes, right? You did it last year. You type in the boxes. If I type 430.1, it's not going to match up with the 428 that's in the background, right? So I have to be thoughtful of that when I'm using intermediate values and rounding them, okay? Pay attention to the question when it says round to the 10th place. Know that what you do with intermediate values is not going to impact the 10th place, okay? I think that's a pain in the butt to do, okay? And I think it's a pain in the butt to teach, but understand why we have that situation, okay? There are people that are writing these tests that think you need to take these tests that are not teachers. They've never been in a classroom. They're business people. They're lifelong politicians. They don't know how a classroom operates in the dynamics of this. Does that make sense? And they don't understand how that can create, somebody that might be a person between a 2 and a 3 might miss out by 1 point because of a rounding error that shouldn't really have made them miss a point. Does that make sense? I want to make sure that you're not a person that gets in that situation, so where you had to take this test again because you missed out by 1 point, 1 question point, because of a rounding error issue. So just be very, very careful with that. Yes?
Well, I'll check how many days would it be good?
4. But you're going to get only 1 day with me.
Why are we sending us to the gym?
Huh?
Why are they sending us to the gym? CPR. We have to learn CPR. Joel told me that we had to learn it because they couldn't fit everyone into English and math, so they created CPR.
Well, something good to know, right?
Well, yeah, apparently everyone's required by law to know it or something.
I mean, a lot of I have to know CPR to be licensed to coach and stuff like that, and a lot of businesses make you if you're a truck driver, you have to go through CPR and learn CPR. So there's a lot. I mean, just an example. There's a lot of businesses that make you go through training for CPR because you never know when you're going to need it. I want to get into, so that example, I'll post that online if you need to talk about that or go through that video again. It'll be posted here in a little bit. In the next half hour or so, guys, I want to talk a little bit less than half hour. I want to talk about perimeters and areas of shapes that are similar. Okay, you guys remember what similar shapes were? Okay, so all the angles are the same, but the sides were different, right? So it's the same shape, but different sizes. And now the sizes were all in ratio to one another, right? They're all proportional to one another. So it's the idea if I've got 2 shapes that are both triangles, maybe one is twice as big as the other one, right? Or one is 3 times as big as the other one, or one is 2/3 the size of the other one, that kind of thing. So we talked about scale factors. It's the dilation aspect of things, right? So we've talked about these things before. We've actually talked about this first concept that I want to kind of introduce to you back in chapter 7. Okay, but it's been a while. But I want to make sure that we understand why this is true. If I were to take a figure here. Let's just say it's a triangle. And I say that this side is A. Let's say that this side here is B. And let's say that this side here is C. And let's say that I give you a scale factor of D. Okay? A scale factor of D. What are you going to take this by, or what are you going to do with this A to come up with this side here, if these two shapes are going to be similar? You're going to multiply it by that scale factor I gave you, right? So I'm going to say scale factor, or the dilation factor, I'm going to say is D right now. So if I multiply this by D, I get A times D. What am I going to get if I multiply this by D? BD, and what am I going to get here? CD, right? Okay, so we're good with that. Is everybody all right? Now, if I ask you the perimeter of this shape here, the perimeter is going to be what? A plus B plus C. I'm just going to call that perimeter 1. What would perimeter 2 over here be? Okay. So initially it's going to look like that, right? But each one of these has a what in it? A D. So can I factor that out? Say D times A plus B plus C. Does that make sense to everybody? Okay. Now, if I wanted to talk about the ratio of perimeters, ratio of perimeters, this would look like P1 over P2, correct? P1 is A plus B plus C. P2 is D times A plus B plus C. Now, understanding what A, B, C, and D were. A, B, and C were just numbers, right? They represent side lengths. Okay? If I have A plus B plus C on top and I have A plus B plus C on the bottom, what are they going to do to one another? Cancel out. And what are you left with? So let's say A plus B plus C, and it'll be in 13. If that would be 13 too, right? So those are going to cancel, and you're left with just 1 on top and D on the bottom, right? Does that make sense to everybody? Well, let's look at how this side compared to that side. What is A compared to AD? 1 over D, right? How does B compare to BD? 1 over D, isn't it? How's C going to compare to CD? 1 over D. That comparison of A to AD, is that your scale factor? Does that make sense to everybody? So do you see here that your scale factor of the shape is exactly the same thing as the ratio of your perimeters? Okay, so that's the first thing. That's a proof of this. That's a proof of this first statement here. That if, and now this similarity ratio, that's kind of a synonym for scale factor. And we also saw it as a dilation factor earlier. Okay, so those are all synonyms. Okay, but if the scale factor, similarity ratio, or dilation factor is A over B, then the ratio of your perimeters of your two similar shapes is still A over B, because of that process of being able to factor out that amount, that scale factor in terms of your perimeter, that larger figure. Okay, so ratio of perimeters is the same thing as your scale factor. Is that okay? Okay. The ratio of your perimeters is the same thing as the scale factor. Okay. So, I'm going to come back to this. If you haven't got that written down, I'll come back to it in a moment. But let's look at this slide right here. I would. If I look at this slide right here, what's the similarity ratio? What's the scale factor of the top shape to the bottom shape? Okay, so it's 9 over 6, 3 over 2, 1.5 over 1, something like that, right? 3 over 2 is probably the one that we're going to kind of stick with. Okay, that's the version that's the best. Do you have the ability to find the perimeter of either of those shapes? How?
Magic.
Do you even know what those shapes are? They look like trapezoids.
We don't know.
But we don't know. Okay, so they're trapezoids. Do you know if they're right trapezoids? Do you know if they're isosceles trapezoids? Do you know any of that stuff?
No, they're obviously
Okay.
not right.
So what I'm saying here is that you don't know enough. Even though we do know they're trapezoids, you don't know enough to be able to work through and find the missing 3 side lengths. So can you find their perimeters? No. But if I can't find their perimeters, I should still be able to know, even though I don't know what their exact perimeters are, I should still know what they relate to one another as. They're going to be 3 to 2. Does that make sense? Okay. Even though you can't pinpoint or nail down exactly what that top perimeter is and exactly what that bottom perimeter is, you know whatever they are, they're going to divide out to 3 over 2. Because that's what that initial proof that we did with the triangles told us. We can do that proof of the triangles with a quadrilateral, any shape we want to. Okay? So the similarity ratio is 3 over 2. The perimeter ratio is 3 over 2. Okay? Now I want to do a practice of dealing with this last bullet here. It says the ratio of areas is a squared over b squared.
What kind of trapezoids were they?
Just trapezoids. Just general trapezoids. All right, so the ratio of the areas is a squared over b squared. Okay? Sometimes you might see that written as a over b, the whole thing squared, because of our laws of exponent rules. We can transform between either of these. I want you to see this relationship. Okay, so we'll kind of do the same process. Let's do this. We'll do a similar proof as what we did at the beginning, but we'll use specific values. It's a little bit easier to see. Give me a number. 7 is what? Give me another number. Let's use 13. 82 is going to be hard to multiply.
Fine. Never learn if you never use it.
All right, let's say our scale factor is 3. Okay? So if this is 7, so these two rectangles are going to be similar. If this is 7, what's this side here going to be? 21. What's this side here going to be? 39. Okay? Now, how big, what would be the perimeter of this shape here? It'd be 40, right? Okay? What's the perimeter of this one going to be? Okay, well, it's because 21, 39, 60, right? So double that, I get 120. If I compare P1 to P2, I get 40 over 120. What's that reduced to? 1 over 3. Isn't that the scale factor? Wasn't this, if I go 7 compared to 21, isn't that 1 over 3? So you see there is a specific example of the ratio of perimeters related to one another. Let's talk about their areas. Okay, if I take the area of this thing, 7 times 13, was that 91? Okay, now, what's 20 times 39? What's 2 times 39? Okay, it's 78, right? 2 times 39 is 78. So 20 times 39 would be 780, right? Add 39 to that, what do I get? It'd be 89, right? You see how what I did there? I took 21 times 39 is equal to 20 times 39 plus 39. Is that still 21 39s? Yeah. Okay, so what we say it was 819? Yeah. Okay. Take 21 times 39. What do you get? 21 times 39, 819. Okay? So I'm trying to show you how to do that kind of mental math a little bit quicker than just grabbing your calculator. Now, if I compare area 1 to area 2, 91 over 819, that reduces to not 1/3. Let's do this. Let's take our calculator. It's a little bit harder to do. I go 91 divided by 819. What's that decimal change into as a fraction?
1/19.
1/9. If I didn't realize that, could I do this? I go 819 divided by 91. Whoa. 819 divided by 91 gives me 9, right? Okay. So 1/9 is what this reduces to. How does 1/9 relate to 1/3, which was my scale factor? If I take this thing here squared, I get my scale factor of my ratio of my areas. Okay? So, whenever they tell you your scale factor is 1/2, your perimeters ratio is 1/2, your areas ratio is 1/4. If I tell you do another example here that I've got written out. If I tell you if your scale factor is 5/7, your ratio of perimeters is 5/7, your ratio of areas is 25/49. Is that pretty straightforward, pretty simple to do?
Yes.
Okay. Now, let's kind of talk about maybe why we can do this. Okay, let's go back to this picture here. If I go with this picture here, what's the ratio of their areas? Similarity ratio is 3:2, right? Perimeter ratio is 3:2. Area ratio is 9:4. Okay, you square the 3/2, right? Okay. What that means to us, guys, is that if I took, let's say that these are like ceramic tiles. What that 9/4 means to us is that if I took 9 of those smaller tiles and laid them down, and then I took 4 of the larger tiles and laid them down, what does that tell you about the two areas that those sets of tiles just encompassed? They're the same area. Okay? Does that make sense? Okay? If you were to, go to Lowe's, go to Lumber Liquidators, go to a carpet store, something like that, all of their information they provide you in regards to prices is all going to be off of square feet. Does that make sense? Square feet, square yards, square meters, something like that. Okay? They'll say, usually when you do let's say hardwood flooring, they'll say it's like $5.25 per square foot. Well, what do I do with that $5.25 per square foot if I have 1,500 square feet in my house? I times 5.25 times 1,500 tells me the price of that I'm going to spend on that hardwood floor, right? Does that make sense? Okay. So I multiply. That's what's going on here. So they're using that 1 square foot as their base standard, okay, to say that 1 square foot then is similar to 1,500 square foot. Does that make sense, everybody? Okay. So, do an example here. It says the similarity ratio of 2 triangles is 3:2. Similarity ratio is 3:2. That's another way of saying the scale factor is 3:2, right? Scale factor is 3:2. That means A over B is what? 3/2. So A over B is 3/2. Okay? Says the area of the larger triangle is 36 centimeters squared. Find the area of the smaller triangle. First thing we need to know is that we're trying to find an area, right? So if you're going to try to find an area, you need to use a relationship that is true about areas. The 3/2 is not about areas, right? The 3/2 are linear dimensions. Area is a square dimension, right? Or a 2 dimension. Okay? So what do I need to do with this A over B to actually address finding area? Okay, so I got to figure out A squared over B squared, which is going to give me 9/4, right? So 9/4 is now the comparison of my two areas. Okay? One of them is 36, and that's the larger one, right? The second aspect of this is that when I'm done, the number I should get should look like what? If 36 is the largest triangle, I'm sure I should get a number that is smaller than 36. Okay? So, I'm going to take this number here, 9/4. That's how my areas compare. Now, I don't know what my areas are, but they compare a 9/4 ratio. I know one of them is 36. Why would I put 36 up top? Because it's the biggest one, right? And the numerators have to have something to tie them together. In my numerators, the 9 Remember what we talked about when we talked in Chapter 7 about similarity and proportion, is that the 9 was originally a larger value. The 4 was originally a larger value, and they shrunk because they had a common factor that canceled out. Okay? So, and I'm comparing 9 and 4. Obviously, 9 is bigger, so the value that 9 shrunk from had to be bigger than the number that 4 shrunk from. Does that make sense? That's what we're looking for. We're looking for the unknown value that this 4 was when it was reduced. So I cross multiply. So we have 9x. Okay, is equal to 144. So x is what? 16. So that means that smaller shape had an area of 16.
Well, if you divide 9 by 36, so it's 4, and then 4 times 4 is 16.
That's a better way of doing it. I would go, so what Riley is saying is if I go 9x, instead of actually multiplying 4 and 36, okay, you could do it several places. You've probably seen this done. Make that a 1, make that a 9, right? Okay. What do we do here? No, sorry, we can't. Let me do it this way. So if I go 36 times 4, I just imply the multiplication. I don't really do it. Okay? Now, if I divide by 9 here, divide by 9 there, that's where you're seeing the 36 over 9 is 4, right? And 4 times 4 is 16 that way. That's the way I prefer to do it. Okay? Say again?
You don't have to imply it to multiplication.
Okay, so you can do it in your head. That's fine. Now, let's look at this. Let's look at this 16. So we had one area with 36. That was the larger one, right? The smaller one was 16. What do they have in common? They have a 4 in them, right? Take a 4 out, you get 9. Take a 4 out, you get 4. Do you see that 9/4 came from two larger values of 36 and 16? Okay. Now, if you would have messed everything up, you would have messed your proportion up. Let's do this real quick. Because this happens all the time. I get people who do this all the time. They go, I know I got 9 over 4, and they put x over 36. If I go 4x equals 9 times 36, isn't that going to be x is equal to 9 times 9? Which gives me 81. If you solve that, you get x to be 81. How do I know that was wrong?
That's bigger than the larger triangle.
Right, that's bigger than the larger triangle, so if I get something like that, logically, hopefully you realize just flip the x over 36 fraction, or the 4 over 9 fraction, and you'll have the right answer then. Okay? Now let's talk about a reason of why maybe this is useful for us. Small triangle 16. Now we just found an area of a triangle by not having to go 1/2 BH, right? Okay, we didn't know what 1 or what B and H were for that one triangle, or either triangle. All right, let's look at this. It says this lady plants the same crop
every day
in 2 fields. Okay, 2 rectangular fields. It says each dimension of the larger field is 3.5 times the dimension of the smaller field. Okay, when they say dimension, they're talking about length and width, right? Or base and height. So if this one is, A and that one's B, this one here is 3.5A and this one's 3.5B. Does that make sense? Okay. If I compare those, it's A over 3.5A. Isn't that 1 over 3.5? That's my scale factor. My scale factor is 1 to 3.5. Okay? So my A over B is 1 to 3.5. Now it says she goes through and she seeds the field. She seeds the smaller field. Okay? And it costs her $8 to do that, right? Now when you're seeding something, are you talking about just seeding the border? No, because the border would be the 1 over 3.5 number, right? Or ratio. You're seeding the interior as well. So you're seeding the area. Okay? So the area is A squared over B squared. It'd be 1 squared over 3.5 squared. Does that make sense? Okay. That's my A squared over B squared. Now it says the cost of seeding this first field, the smaller field, was $8, right? You see how that link between the numerators was that it was information from the smaller field, right? I want to know what it costs to seed the larger field. Can I cross multiply those? I get 1x is equal to $98 if you cross multiply that. And that tells me now it costs me $98 to seed the larger field. Okay? If you were to go to Lowe's and look at grass seed, it'll have information on the back of it like this. If you go buy concrete, every bag will have information like this, usually in volume though. If you go buy flooring, if you go buy mulch, all that stuff, okay, in regards to areas that incorporate a concept of areas, are going to have this type of information on it that you can use to project costs. Okay? And, you know, if you're going to pour a driveway in concrete, or a patio in concrete or something like that, you do not want to go buy 90 bags of concrete on a whim when maybe it only takes you 50 to do the project, right? Now you got to ship back 40 bags of concrete or somehow get them back to the store, right? You don't want to, you know, go buy 90 bags of concrete and have that delivered in a Lowe's or Menards charge of delivery is like $200, and then find out, oh, I needed 40 more bags. I need to spend another $200 for them to deliver another 40 bags, right? So you, in order to kind of prepare for a project, these are the kind of things mathematically that you would go through from the information that's provided on a bag of concrete or a bag of seed or something like that. Okay? 10-4 is available online, due on Tuesday, 10-3 is due on Monday.
Please pardon the interruption. Students that have principals with suits, this is a reminder for you to go to Mrs. Brayshak's room this afternoon.